Hello everyone, I'm Moses Eleni from WAP. Today I will be talking about the lepton flavor violation Higgs decays in the Scotogenic model. Okay, first of all we need to know that we have upper bounds for the branching ratio of the lepton flavor violation Higgs decays. Experimentally, for example, we know that the Atlas reports that the branching ratio of the Higgs to E tau and mu tau are of the order of 10 to minus 3. This result is really important, and also we expect that in the future these upper bounds improve in 1 or 2 orders. Also, new physics models often include a Higgs boson with near futures. For instance, this can induce flavor violating Higgs couplings at 3 level, as in the case of the 2 Higgs doublet model, or they could be induced at loop levels, as in the minimal supersymmetric standard model. Well, we are interested in this case in the Scotogenic model, that in comparison of the standard model, this model includes a discrete symmetry Y2, and also we include right-handed neutrinos and a second Higgs doublet inner. These new particles are odd under this new symmetry, and the standard particles are even under this symmetry. The main purpose of this model is the inclusion of the neutrino masses and a dark matter candidate, and then this Y2 symmetry allows a stable dark matter candidate. In the Yukawa sector, with the content of matter in this model, we can construct a Dirac term for the right-handed neutrinos and the second Higgs doublet. However, this second doublet is inner, then we don't have a neutrino mass term at 3 level. Also, we can induce or we can construct the Majorana term from the right-handed neutrinos. In this case, the more general scalar potential under Y2 symmetry is given by equation 2, and together with equation 1, the new interactions induce that the neutrino masses are generated by a radiative seesaw mechanism as given in equation 3, and in this case the lambda key depends on the masses of the right-handed neutrinos and the masses of the real and imaginary part of the neutral scalar of the inner doublet. For simplicity of the evaluation of the branching ratio of the lepton flavor violation Higgs decays, we choose the basis where the Yukawa matrix G prime is diagonal, and as a consequence the neutrino mass matrix is also diagonal. Then we can rewrite this Yukawa matrix as is given in equation 4, and then we expect that all the mixings in the leptonic sector comes from the charged lepton sector. Then finally, in the physical basis, the new Yukawa couplings for the interaction between left-handed lepton doublet and the singlet neutrino is given by equation 5. Well, the most important interaction for the lepton flavor violation Higgs decays are summarized in this table. In this table, we can observe that we have two kinds of interactions: the interactions of only standard model particles and the interaction of the standard particles and inner particles. The interactions of the Higgs and inner particles, or the charged scalars and leptons, induce the following three diagrams that are showing here. These three diagrams contains heavy neutrinos and the charged scalars. We also can paint the diagrams where light neutrinos participate. However, these neutrinos have a really small mass, then these diagrams are neglected. For the numerical analysis, we need to consider three main constraints. First of all, the relic density of dark matter, consider that N1 as the dark matter candidate, and also we need to consider the constraints that comes from of electroweak parameters and the experimental upper bound for radiative decays mu2 A gamma. With these constraints, we need to assume that the mass of the dark matter candidate and the masses of the inert scalars must be of the order of 10 to 2 GeVs, and the lambda 5 is around of 10 to minus 10. For heavy neutrinos, we also assume that the dark matter candidate mass is really small in comparison of the other two heavy neutrinos. Then we fix that M2 is equal to 10 to 4 GeVs and M3 is equal to 10 to 5 GeVs. Finally, we fix mu2 equal to 1 GeV without loss of generality. Well, in this plot, we illustrate the behavior of the branching ratio of the lepton flavor violation Higgs decays in the vertical axis, and in the horizontal axis we have the masses of the dark matter candidate. We consider two cases for this plot. One of the first case where the masses of the scalars are around of 800 GeVs with solid lines and also are labeled with 800, and the second case with where the masses of the scalars are around of 200 GeVs, which are in dashed lines and also are labeled with 200. We can observe that this plot illustrates that the branching ratio grows with the mass of the charged scalar or the scalars, the inert scalars in general, and that when the mass of the dark matter candidate increase, the branching ratio decrease. Well, we need to observe that the largest value of the branching ratio are of the order of 10 to minus 7 for dark matter mass of the 100 GeVs. In the case of the scalar masses of around of 800 GeVs. Also, finally, we need to remark that by the electroweak parameters constraints, the masses of the scalars are really together. Well, then the first conclusion was that the branching ratio reached values of 10 to minus 7 for the mass of the dark matter candidate around of 100 GeV, and also that the second conclusion is that although the branching ratio or the scale of the branching ratio of the lepton flavor violation Higgs decays in the Scotogenic model is small, still in comparison that the result that we obtain in the standard model is really big in this case. Finally, these results are in agreement with the approximations of the reference 2 and 3, and well, we show finally the reference that we consider for this work. Finally, in the description of this video, I will share with you my Python code for the evaluation of this lepton flavor violation Higgs decays in the context of the Scotogenic model. Thanks.